Okay, so let's try to connect these things. Anyway, it's hard, and I just want to, I mean, that's a fun thing, but it is hard to make. I mean, we have these fractal generators for landscapes and so on, but that was kind of an impressive adjustment. In terms of like actual research, it's hard to make a landscape that then you can erode in a room like this and get real kind of network structures out. So people have gotten somewhere with that, but that's a hard thing to do. Okay, so I'm going to try and connect these. I know I'm taking a long time, but I'm going to connect these scaling laws. This is just to sort of start this section off. This is a paper that appeared, as you can see, 2014, just a few years ago, that tackled this. We have this, as I said, this problem. We don't have the history of the evolution of a landscape, right? Because we just don't have a way of. We don't have satellite data from 10,000 years ago, because we're just too stupid to have invented it by then, or whatever, right? So it's hard to see how these things have changed. But you can get in there and say, I think you can. This is okay. So piracy on the high keys, right? This is a terrible pun of mine, but piracy is a word that people use in geomorphology, talking about these things. I mean, look at these. This is to try and make it more exciting for themselves, because it really isn't. But there's an aggressor and a victim. I mean, this is just unbelievable nomenclature. Anyway, but the idea is, there's a divide here and there's stuff going this way, and it's going to eat into this divide. It's going to be steeper on this side, and there's going to be more erosion, and this is going to balance itself out. Right, so and we talked about it a lot with hot models and lots of other things in POX, right? So they're sort of, there's a really fundamental story to a lot of systems is equilibrium, right? And that's been a big thing. But then there can be equilibria in dynamic systems that are about other pieces. And for, say, the hot model, it was creating structures that minimized risk, or in the sense that they're distributed evenly. And so this is a dynamically evolving landscape. But there's something going on that is going to move it towards a kind of an equilibrium type structure. There's no risk or anything. It's more of a simple kind of traditional physical system, I suppose. Anyway, this is an effort to sort of see the history of things and actually kind of try and tease out some sort of evolution. But this is the basic idea, right? So you do the sort of thing that we described at the start of this lecture, which is to find out where all the networks are, and of course you have these slopes and so on, right? So you can start to think about how strong the erosion might be, right? If it's really shallow, then you expect erosion to not be as strong. There are some, this is all a bit of madness. There are some odd heuristic things that people have come up with. It's very rough, but basin area is roughly correlated with slope, and if it's not balanced properly, then you can sort of assert that things get out of control. That's what this funny little measure is here. You don't have to worry about these too much. Okay, so there was some other pieces in here. Will it? Oh, okay. This is just 2 minutes. All right. Yep.
To most of us, river networks appear to be fixed features of the landscape. In fact, many rivers define political boundaries that have been in place for centuries. But what if those boundaries are moving? Scientists have long suspected that river networks are not as static as they appear. Some rivers look distorted, and others contain rocks or aquatic organisms that can only have come from other rivers that aren't currently attached. This suggests that rivers have been shifting and moving across the landscape over millions of years, but until now, there has been no way to measure this change. Researchers at MIT and the Swiss Federal Institute of Technology have developed a mapping technique that measures how much a river network is changing and in what direction it may be moving. The technique focuses on a river network's drainage divides, the ridgelines that separate two neighboring river basins. As rainwater flows down either side of the drainage divide and into opposing rivers, it erodes the underlying rock, creating an imbalance in the river network. To reach a balance, the drainage divide must shift to assume a more stable pattern. With this new measuring technique, researchers can determine the direction in which a divide would have to move to bring its river networks into balance. Knowing where river systems are shifting may help scientists understand how these rivers shifted, diverged, and merged over millions of years. This knowledge may help solve some long-standing mysteries in geology and biology, such as why some rocks and fish that seem to belong in one river basin are also found in another.
So that was, that's a little press release type thing, just for a couple of minutes from MIT. But this was really impressive. No one had been able to do anything quite like this, and seems to have some good legs to it.